Okay, this is the first Gurobi lecture. So, like before, I'm going to start off by clicking on this link, getting these example codes on GitHub. And again, if you've never used Git before or GitHub, maybe the easiest way to get started is just to download everything here as a zip. So you may have already done this, but I'm going to go ahead and do it again. Okay. So I've downloaded that zip file of everything in the repository. I unzipped it, and then we're going to be working in this starters folder. And if you just downloaded it, you may have to use my network JSON file over into the starters as well. If you've watched all the Network X videos, you should already have this file. It should have been already generated. Okay. So I'll open up Jupyter Notebook. Let me close the one that I have now. Okay, so I'll go to wherever I had saved that code, which in my case, I just left it in the downloads folder. Okay, and again, I'll go to the starters folder. And the first one that we're going to do is Gurobi shortest path. Okay, so previously we saw how to solve shortest paths in, I guess, using functions from Network X. Today we'll do the same thing, but modeling this as an integer program, or potentially as a linear program. So I've already defined these things in the cell for you to read this network. So, okay, so our file name, the file that we're going to read in is mynetwork.json. Then we will use this function to read in that file. Read in that file name. And then just to check that it read in properly, we'll just go ahead and print the nodes and in the edges. Okay, so this graph has nodes 1 through 8, 1 through 8, and then some of the edges 1, 2, 1, 3, 1, 4, 1, 2, 1, 3, 1, 4. It seems like everything read properly. Okay. So when we're writing the integer program for this problem, we'll need to refer to the in neighbors and the out neighbors of a node. So node 1 only has out neighbors. So its out neighbors are 2, 3, and 4. Node 8 only has in neighbors, 7 and 6. And a node like node 3, it has in neighbors 1 and 2, and out neighbors 5 and 7. Okay, and if you'll remember from our model, we're going to essentially send a unit of flow from our origin to our destination. So the outflow of our origin is going to equal 1. So essentially we'll pick one of these edges that points out of 1. And then our destination, we need to have a flow of 1 incoming to it. So essentially we're going to pick one of these edges to be essentially the end of our path. Now every other node in our graph is going to have flow balance. So essentially if we enter a node, then we must leave it. So the number of in arcs is going to equal the number of out arcs that we pick. Specifically, in this case, it should either be 1 incoming and 1 outgoing, or 0 incoming and 0 outgoing. Okay. Now, in order to write those constraints, we're going to need we're going to need to know how to refer to the in neighbors and the out neighbors using network X. Okay. So for each one of these nodes, for each I in b dot nodes, we'll want to print the in neighbors and out neighbors. So node I has in neighbors. Then I'll print the in neighbors, which I would like to refer to something called in neighbors of I, but unfortunately, this isn't how network X has named this. So network X refers to predecessors. Of I and out neighbors. So I would like to write out neighbors, but again, network X isn't using this naming convention. It uses successors. These and two S's. All right, let's see if that will print. Okay. And it throws this kind of nonsense here because these are actually network X is keeping these stored as iterators, not as an actual kind of explicit list. So if I wanted to print everything in this predecessors, I would need to convert it to a list. Okay. So now if I rerun that cell, it seems to be working properly. The node 1 has no in neighbors, and it has out neighbors 2, 3, 4. Node 8 has in neighbors 6 and 7, and no out neighbors. And node 3 has in neighbors 1 and 2, and out neighbors 5 and 7. Okay. So let's model this shortest path problem, and we're going to solve it using Gurobi. So to get Gurobi, we'll import Gurobi Pi as GP. And then we'll also use something else in Gurobi Pi called GRB. So from Gurobi Pi, import capital GRB. And if you don't know, the reason why this optimization solver is called Gurobi is because of the three developers, the three kind of co-founders. So their names were or are Berg, Gu is Songhao Gu, Ed Rothberg, and B is Bob Bixby. Together, Gurobi, and then I guess also this GRB right here is just their initials. Okay. So, okay, so we've got Gurobi now imported. So we'll create a Gurobi model object, which I'm going to call M. And this will be, I'll get this by calling gp.model. And then I'll create my variables. So I'm going to call those variables X. Add to my model these variables. And I want to create one of these binary variables for each edge. So essentially it's indicating, do I traverse that edge in my path or not? So I'll create a variable for each edge. And each of these should be binary. So the variable type is GRB binary. Okay. All right, so anytime you're talking about the shortest path problem, we want to specify where are we starting our path and where are we ending. So in our problem, we suppose that we're starting at 1 and we're ending at 8. I'll use S and T to denote that. And then our objective function is to minimize the essentially the weight of each edge multiplied by the decision to include the edge. So I'll m dot set objective, and the first argument is going to be what are we minimizing or optimizing, and then the second argument is going to be whether we're minimizing or maximizing. So in our case, we're minimizing. And on the left side, we'll write our objective, and we're going to be summing a lot of things. So I'll use this gurobi.quicksum, gt.quicksum. So inside of here, I'm going to write that I'm minimizing something times xij for all of the edges ij. So I'm summing over all arcs ij, and I'm summing not just the x variables, but I need to multiply by this by the weight of the edge, which, if you'll recall, this is g dot edges ij, and then the attribute for the weight that I'll explicitly have to multiply using this asterisk. Another way that I could write this, maybe this is a cleaner way, is instead of using ij, I could just use e. Oops. Little e. I'll do that. Okay. So I've defined my model, I've defined my variables, and I've set my objective. So now I just need to add constraints and then solve. So our first constraint is that essentially we need to pick one edge that points out of S. So I'll do m dot add constraint. And I want to say that we pick one edge outgoing from S. So I could say equals 1, and then on the left I'll have my sum. But actually the way that we wrote it in class is we write incoming edges minus outgoing edges equals -1 for S. So incoming edges for S will be 0. Outgoing will be 1. So then we'll get -1 equals -1. Okay. So to express incoming edges, now for this particular graph, S has no incoming edges. So in some sense, I don't need to write this for S, but it'll be convenient that I'll write something here and then I'll kind of mimic the style for the other nodes. So I'll just go ahead and write it generically like this. So I want to write, I want to look at all edges that are of the form j to s. This is for all j's that are in neighbors of s. So for all j in d dot predecessors of s. Okay. So this is the sum of those x variables for the incoming edges. And then I'll want to take essentially the same thing, subtract, but now I want successors. And I guess I also need to specify this is not j to s, but actually s to j. Okay. Now the other nodes that aren't the origin s and aren't the destination t, I want, for them, I want incoming edges minus outgoing edges equals 0. I want that flow balance. So either this is 1, in which case this should be 1, so you come in and then you must leave, or you don't enter that node at all, so this would be 0, in which case this should also be 0. So fortunately, given I wrote out that previous constraint quite generically, I can copy this and modify it. So one difference here is that I'm writing this constraint for lots of nodes, not just one node. So I actually have multiple constraints with an S. So I'll put an S right there. And then I want to write this constraint for every node I. So this is not going, these edges aren't going to S, they're going to I. So these are predecessors of I. And then these outgoing edges, they're not S to J, they're I to J. And these are all for all J's that are successors of I. And I want this to have flow balance. I want this net flow to be 0. And then I also need to specify that this is for all I. So this is for all I in P dot nodes if I is different than S and T. So I could write if I not in the set ST. Okay. So this constraint is quite long. If I wanted to, I think I could do that, a hard return, and then the text wouldn't be so wide. I'm just going to leave it as is, but I would completely understand if you wanted to have a return there. Okay. And then I could just run this cell and add these constraints. But you'll see here that it prints essentially the names of these constraints, actually the last operation that I did. So it adds a constraint for nodes 2, 3, 4, 5, 6, and 7, which is everything besides 1 and 8, the origin and destination. So if I didn't want Gurobi to print all of this information every time that I added constraints, I could just do in.update at the end of that cell, and then it wouldn't print this information. Okay, so I think that does it for the constraints. I could, if I wanted to, I could add another constraint for the destination T. So it would look just like this constraint, but it would be for T. And that right-hand side, instead of it being -1, it would be +1. Okay, but I don't need to. In fact, these constraints will suffice and will make that to be true automatically. Okay, so now I'm ready to solve. So I'll do m.optimize. And you'll see we have 11 integer variables, which in fact all 11 are binary. They're all 0, 1 variables. I have 0 continuous variables. And so let's just double check. So since we have 11 binary variables, we should check that we have 11 edges in our graph. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So that checks out. Let's see. So variables are columns. So we have 11 columns, 11 variables. And it says we have 14 rows. So let's see. So why would we have 14 rows? I think we have this constraint at S once, and then we had constraints at these other nodes that aren't S or T. So that'd be nodes 2 through 7. So in total, I think we had 7 constraints, but it's showing that I have 14 constraints. And I think what happened here is I ran this cell twice. So it added these constraints, these exact same constraints twice. So ultimately, it doesn't affect the feasible region or an optimal solution in any way, but it's just kind of a larger model than need to. If I wanted to, I could go back and just recreate this model at the objective and constraints just once. And then, now I should have those 7 rows or those 7 constraints in my model. Okay. So you'll see that Gurobi solved quite quickly. It actually, in its pre-solve procedure, so even before it solved the LP relaxation, it just did some tidying to the model, and it actually removed all of the variables and constraints from the model. So just some simple pre-processing, it was able to find an optimal solution with objective 32, which, if you'll recall, that's the length of a shortest path from node 1 to node 8. So we could print what are the values of all of our variables. So for every edge ij, or I could even say for edge e in p dot edges, I'll say that x of edge e equals, then I'll just print x of e. Now, one thing to be careful here is that xe is actually a variable, but I want the value of that variable. So I need to do dot x here. So I can only call this after I've solved. Okay. So it looks like I've got my 11 variables here, and they're all 0 or 1. Okay. So if I wanted to get the edges that are part of this path, I could say chosen edges equals, and then I'll create a list here. I'll say this is all edges e, for e dot edges, for which x e dot x, and I would be tempted to say equals 1, because these are supposed to be binary variables. However, I would definitely encourage you not to write this. And the reason is that when Gurobi is solving, it's working in floating point arithmetic. So all of these variables, even though we've defined them as binary, Gurobi is going to be solving LP relaxations, and it may get something like 1.00000000001. And if it's slightly different than 1, this would not catch it. So Gurobi is going to look at that number, or 0.999999999, and it'll say, yeah, that's supposed to be 1. That's integer, and so it'll stop, and it'll actually return to you that 0.9999999 number. So really, what a safer check to do here is just to check if this is at least 0.5, and that'll be much safer. Chosen edges, I could go ahead and print what those chosen edges are. So 1 to 3, 3 to 5, 5 to 6, and 6 to 8. So I believe that was the same path that we had seen before. Now, only one thing I should mention here: these edges are going to be printed in the order in which you kind of define these variables. So we have a list of edges. They're kind of stored in this graph D, and they're stored, I think, in that original order that we had defined this graph in. So I think they're all given lexicographically. This may not be the order in which the edges are followed in your shortest path. So this is just going to print the chosen edges, but maybe not in the right order. So maybe I should specify here, chosen edges are not necessarily in order are. Okay. So if you recall, in class, I had mentioned that the LP relaxation of this model had a very nice property. The constraint matrix is totally unimodular. And in essence, what that means for us is that if you were to solve the LP relaxation, it would actually give you an integer solution for free. So we don't have to necessarily define these variables as binary. So in fact, if I were to take the LP relaxation, which I could get by doing m dot relax, and if I were to solve this relaxed model, you'll see that I get the exact same objective value, which I could query this by saying the relaxation objective is, and then r dot objective value. So it's also 32. So the objective should be the same, and assuming the optimal solutions are unique, it should give you the exact same solution.